Hello everyone. So let's now solve question number 4. So the question 4 says, choose the correct set of options based on the matrices given in the table. So we have 4 matrices in each column, column A and column B. And if we look at the options, they are asking us to find the inverse of these matrices. So for any matrix of order n cross n, if we want to find its inverse, then that is given by the formula adjoint of matrix A divided by its determinant. So using the formula, we will try calculating the inverse of each matrices in column A and try to match with these matrices with column B. So let's first calculate the inverse of for matrix A. For matrix A is this matrix. So let's note down A1, 1, 0, 1, 0. Now we will try calculating the adjoint of matrix A. And adjoint for any matrix is given by the transpose of cofactor matrix, where cofactor matrix is just the matrix of containing all the cofactors for a matrix at the ijth entry. So for calculating the cofactor, we will use the formula minus 1 power I plus j times minor at ijth entry. So for example, if you are calculating cofactor at 1/1th point in entry, then we will eliminate the first column. We'll get the sum matrix. We will calculate its determinant. So the determinant of this sum matrix is minus 1. So minus 1 power I plus j. So minus 1 power I plus j times this minor is actually given by the determinant of its sum matrix. So the sum matrix has determinant minus 1. So we are calculating in 1/1th entry. So it would be 1 plus 1 times minus 1. So that would give us minus 1. And similarly, let's say if we are calculating at 2/3 entry, then 2/3 entry is this. So we will eliminate second row, third column. We'll get the sum matrix. So sum matrix contains these entries and its determinant is 1. So it would be minus 1 power I plus j times 1. The minor at ij is the determinant of sum matrix. Now we are calculating at 2/3. So 2 plus 3 times 1. So it would be minus 1. And similarly, we will calculate the cofactor at each entry and put them in the matrix form for ijth entry corresponds to the ijth cofactor for the matrix A. So in that fashion, if we calculate the cofactor matrix, then it would be minus 1, 0, 0, 0, 0, minus 1, 0, minus 1, 0. So this will be the cofactor matrix. Now if we do the transpose of this matrix, we'll again get the same matrix. So now as we have found the adjoint of matrix A as a cofactor transpose matrix as corresponds to adjoint for matrix A, then A inverse is given by adjoint of matrix A divided by determinant of matrix A. So this was the adjoint for A1. So adjoint for A1 divided by determinant for A1. So our adjoint matrix was this. So we have to calculate the determinant for matrix A1 also. So if we quickly calculate the determinant for matrix A1, it would be negative 1. I have tried calculating the determinant along this row. So this would be negative 1. So we just have to divide this matrix by negative 1. So the matrix we will get would be 1, 0, 0, 0, 0, 1, 0, 1, 0. So this would be the matrix that is inverse to our matrix A1. So this is A1 inverse. And if we look at the matrices in column B, this is our matrix B3. So our matrix B3 is inverse for matrix A1, and that is what given in option 1. So option 1 is true, while option 2 is false. Now similarly, let's try calculating the inverse for other matrices. For A2, if we look at the matrix A2, it is this matrix. A2 is 1, 0, 0, 0, negative 1, 0, 0, 0, 1. Now first let's calculate determinant of A2. As it is a diagonal matrix, so its determinant would be product of its diagonal. So it is negative 1. Now let's calculate adjoint of A2. For that, first calculate its cofactor matrix. So as calculated before, the cofactor matrix for it would be minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1. And the transpose of this, that gives us adjugate for matrix A2. So C transpose, that is adjoint for matrix A2, is given by minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1. It is the same. So A2 inverse is adjoint for matrix A2 divided by determinant for matrix A2. So our determinant was negative 1. So it would be 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So that is our A2 inverse. And if we look at the option in the column B, it matches with matrix B1. So matrix B1 is A2 inverse. So A2 and B1 are inverse to each other, while A2 and B3 are not inverse to each other. So that's why option 5 is false, and option 9 and option 10 are also false. So that we haven't checked yet. Now let's try calculating A3 inverse. So our matrix A3 is this matrix 0, 0, minus 1, 0, 0, minus 1, 1, 0, minus 2, 0, 1, minus 0, 1, minus 3. So let's calculate the determinant for matrix A3. So I will be calculating determinant along this row, and its determinant would be minus 1 times 1. So that is again minus 1. Now let's again try calculating adjoint for matrix A3. I will directly write now adjoint for matrix A3. 2, minus 1, 0, 3, 0, minus 1, 1, 0, 0. So this is the adjoint for matrix A3. So now A3 inverse is adjoint for matrix A3 divided by determinant of matrix A3. So determinant of matrix A3 is negative 1. So it would be minus 2, 1, 0, minus 3, 0, 1, minus 1, 0, 0. So this is our A3 inverse. And if we look at the column, then B4 is the matrix, that is our A3 inverse. So A3 and B4 are inverse to each other. Option 4 is correct, while option 6 is incorrect. Now let's remaining is F4. So A4 matrix. So our A4 matrix is this. So A4 is 0, 0, negative 3, 1, 0, negative 2, 0, 1, negative 1. So as same as before, first calculate the determinant of matrix A4. So its determinant would be, again I will be calculating determinant along this row. So minus 3 times 1, so that is minus 3. Now let's calculate adjoint for matrix A4. So that would be, now if we are calculating the adjoint, so here the adjoint matrix would be 2 minus 3, 0, 1, 0, minus 3, and 1, 0, 0. So A4 inverse is given by adjoint for matrix A4 divided by determinant of matrix A4, and determinant is minus 3. So minus 2 by 3, 1, 0, minus 1 by 3, 0, 1, minus 1 by 3, 0, 0. So this is the matrix that we got, and if we check from the table, it matches with matrix B2. So this is our A4 inverse. Hence option 8 is correct, option 7 is wrong. So the next four options are about calculating the reduced row echelon form for these matrices. So the condition for the matrix to be in reduced row echelon form are as follows. That is, the first non-zero element in each row is called the leading entry. That should be 1. Each leading entry is in a column to the right of the leading entry in its previous row. Row with all the zero elements, if any, are below rows having non-zero elements. For a non-zero row, the leading entry in the row is the only non-zero entry in its column. So based on these conditions, let's try reducing the matrix first with A1. So n matrix is this. So we can use our elementary row operation to interchange the third row with second row, and then we will get this matrix that is in its reduced row echelon form. As the first condition says, the first non-zero element in each row called the leading entry is 1. So that is 1 for each row. Each leading entry is in a column to the right of the leading entry in its previous column. So if we look at the each column, then for this, the next pivot entry is in its right. For this, also the next pivot entry is in its right. The third condition, that row with all zero elements, if any, are below the rows having non-zero element. So there is no zero row, so there's no point for discussing this. Now for the fourth condition, for a non-zero rows, the leading entry in the row is the only non-zero entry in its column. That means the pivot entry should be the only non-zero entry in its column, and that is indeed the case here. The pivot entry is indeed the only non-zero entry in its column, as all the entry in the pivot column are non-zero except the pivot element, as we can see. So this matrix now in its reduced row echelon form. Similarly, we will try calculating for the other matrices. For A2, we have 1, 0, 0, 0, negative 1, 0, 0, 0, 1. So we can simply multiply the second row with negative 1 to get the matrix in its reduced row echelon form. Now for the matrix A3, that is 0, 0, negative 1, 1, 0, negative 2, 0, 1, negative 3. Now if we try interchanging the second row with first row, we'll get 1, 0, negative 2, 0, 0, negative 1, 0, 1, -3. Now just multiply second row with -1, then we get 1, 0, -2, 0, 0, 1, 0, 1, -3. Now again interchange the second row with third row. We get 1, 0, -2, 0, 1, 3, -3, and 0, 0, 1. Now, till now this matrix is in its row echelon form, as the fourth condition, that is for a non-zero row, the leading entry in the row is the only non-zero entry in its column, is failed for this, as in this row the leading entry is 1, and if we look at, this is not the only non-zero entry in its column. So basically we have to make these entries 0, and that we can make by doing the row operation on R1, that is R1 plus 2R3, and on R3 as on R2 as R2 plus 3R3. So the matrix you will get is 1, 0, 0, 0, 1, 0, 0, 0, 1. So now this matrix is in its reduced row echelon form. Now similarly let's try for A4, 0, 0, -3, 1, 0, -2, 0, 1, -1. So if we interchange second row with first row, we get 1, 0, -2, 0, 0, -3, 0, 1, -1. Now if we again interchange third row with second row, we'll get 1, 0, -2, 0, 1, -1, and 0, 0, -3. Now let's divide R3 by -3. Then we get 1, 0, -2, 0, 1, -1, 0, 0, 1. And if we do R1 is R1 plus 2 times R3, and on R2, R2 plus R3, then we will get 1, 0, 0, 0, 1, 0, 0, 0, 1. So this matrix is also now in its reduced row echelon form. So now let's look at the options, what they are saying. So A2 and A3 have different reduced row echelon form, and option 10 is saying A1 and A2n have different reduced row echelon form. While if we check the reduced row echelon form for our each matrix, for each matrix, its reduced row echelon form that we get is identity matrix. So all the matrices have the same reduced row echelon form. That is option 11, and other options are wrong. Also, one general fact that if we have a n cross n matrix, that is the square matrix, and thus its determinant is non-zero, then the reduced row echelon form for this matrix would be always be identity matrix of the same order. Thank you.